A left-sided limit, and by the way, all of these definitions are going to sound kind of crazy abstract, but when you actually see examples of this is not going to be too difficult at all, I think, to understand. But a left-sided limit, think about a number line. A left-sided limit is the value that a function approaches when you approach the limit point. I'm using this little x0 to represent my limit point here, from the left side of the xy plane. A right-sided limit, same thing, but we're approaching from the right. And you notice the only difference between the notation here is right there. Like for a left-sided limit, we put a little minus sign as a superscript above the limit point. And for a right-sided limit, we put a little plus sign as a superscript above the limit point, because on a number line, all the positive numbers are on the right and all the negative numbers are on the left. So that's left-sided limit, right-sided limit. Whenever we say a two-sided limit, most people just use the word limit. If you just hear limit, then it's referring to the two-sided limit. And so you've got a point, you're approaching this point from both sides, and you're asking, okay, what values is my function approaching as I approach this point from both sides? And if the right-sided limit and the left-sided limit are both approaching the same value, then that's the value of the two-sided limit. If your right-sided limit and your left-sided limit are approaching different values, then we say the two-sided limit does not exist. A function is continuous if you can draw the whole curve without lifting your pen from the paper. But the formal definition of continuous, like what do mathematicians actually say continuous means, is we say a function is continuous on an interval if for every point in that interval the two-sided limit exists, which means the right side is equal to the left side, and the limit is equal to the value of the function. That's the formal, rigorous definition for the word continuous, as in continuous function. If you've got a point where the function is not continuous, either because the left-sided limit and the right-sided limit aren't the same, or because the limit exists, but the function has a different value from the limit, if either of those are the case, that point is called a discontinuity. And discontinuities can come in a bunch of different types. Like, if my function just has a hole in the function, and otherwise it would look continuous, except for the hole, you could just plug the hole, and then you'd have a continuous function. We would say that discontinuity is easily removed, and so it's a removable discontinuity. If the left-sided limit and the right-sided limit are real numbers, but they're different real numbers, so that the limit doesn't exist, then we call that a step discontinuity. If you have a discontinuity where the left-sided limit and the right-sided limit are opposite infinities, so like one's positive infinity, one's negative infinity, that's called an odd pole. If the left-sided limit and right-sided limit are the same infinity, like they're both positive infinity, that's what we call an even pole. And if it doesn't fit any of those descriptions, then we would just call it an essential discontinuity. And so I'll show you examples of all of these, and then the definitions are going to make a lot more sense. Okay, consider the following limit. And what we're going to do is we're going to evaluate this numerically. We're going to evaluate this visually. We're going to evaluate this analytically. We're going to talk about whether the function is continuous there at the limit point. And if the function is not continuous, we're going to try to identify what type of discontinuity is occurring here. And so these are all different types of test questions I could ask you. I probably won't ask you all 5 of these questions. on a test for a given function, but I could ask you one of the 5. So what does it mean to evaluate the limit numerically? What this means is my limit point here is 3. And so the first thing I would try to do is find out what is the value of this function at 3. Right? So if I had 3 squared minus 9, that would be 0. What if I had 3 squared minus 2 times 3 minus 3? Yeah, that's 9 minus 6, 9, so that's 0. So that appears to be undefined. But the next thing I would do if I'm evaluating this whole thing numerically is I would ask, what is f of 3.1? And maybe you need a calculator for this. So you pull out your calculator and you say 3.1 squared minus 9 divided by, open parentheses, 3.1 squared minus 2 times 3.1 minus 3, close parentheses. I got 1.487, 1.488. And then now try f of 3.01. Again, open parentheses, 3.01 squared minus 9, close parentheses, divided by open parentheses, 3.01 squared minus 2 times 3.01 minus 3, close parentheses. That time I got 1.499. And then maybe I try 2.9. So 2.99 squared minus 9 in parentheses divided by open parentheses, 2.9 squared minus 2 times 2.9 minus 3. And oh, I didn't do that right. Okay, gotta try that again. 2.9 squared minus 9 2.9 squared minus 2 times 2.9 minus 3. So 5.9 divided by 3.9 is 1.513. And then the next thing I'll try is maybe 2.99. 2.99 squared minus 9. Negative 0.0599. 2.99 squared minus 2 times 2.99 minus 3 is negative 0.0399. It's going to be 1.501. Okay, so imagine this is like trying to get an estimate of the right side limit, because 3.1 and 3.01 are a little bit to the right of my limit point on the number line. And then this, 2.9 and 2.99, that's trying to get a feel for what the left side limit is going to be, because those numbers are to the left of 3 on a number line. And as you consider, what number are we approaching on the right side? What number are we approaching on the left side? What does it seem like? What does it seem like the limit will be? Hudson?
Looks like 1.5.
Yeah, it looks like the limit might be 1.5. Because these numbers on the right side look like we are approaching 3 from the right side and getting closer and closer to 1.5. Over here, it looks like if I, were forced to take a guess at this, if I'm approaching 3 from the left side, it looks like we're approaching 1.5. And, you can always take more points if you want to. I was just kind of not taking a ton of points because I know we have a limited amount of lecture time here. But as long as you have a calculator, you could do as many points as you want. Like, here's the number 3, and if I try to take my function, which is x squared minus 9 divided by x squared minus 2x minus 3. I can't, right? That was undefined because I was dividing by 0. And then I could start, from the right side and take as many of these as I want. And so you can get as much accuracy kind of as you want just by getting closer and closer on the right side. And then the same thing on the left side here. What we could do is start from 2.9 and then try 2.99 and 2.999 and 2.9999 and 2.92345 and 1, 2, 3, 4, 5, 6. And then the same deal. You can get more accuracy by taking points that are closer to your limit point and just plugging them in your calculator. Does that make sense? Okay. So that's always an option available to you, is evaluate the limit numerically. The next thing says evaluate the limit visually. And so on a test, I will have to give you the picture on a test in order for you to evaluate the limit visually. But for your homework, I didn't give you the picture. I'm just expecting that on the homework. You can pull out your phone or your laptop and you can use Desmos. And we can just type in y equals x squared minus 9. Divided by x squared minus 2x minus 3. And we're talking about, what the heck is the limit of the red function as we approach x equals 3, which is the vertical blue line, right? And so here, imagine I'm approaching from the left side, getting closer and closer and closer. Well, it seems like the limit point would be here, which is like 1.5. And then if I'm approaching from the right side and taking the right sided limit, again, the same thing is like we're approaching the point 1.5. If I actually try to ask Desmos, what is the value of this function at x equals 3? It's going to tell me it's undefined. But again, whenever you go to graph it, it looks otherwise smooth. So that's what I mean by visually. You should be able to look at a graph and tell what the limit is. Evaluate the limit analytically. Here's what I mean by analytically. Maybe you've already done this before in like an algebra class. But let's factor this. How does the numerator factor?
X plus 3x minus 0.
Yeah, x plus 3 times x minus 3. How does the denominator factor?
X minus 3, x plus 1.
Yeah. X plus 1, x minus 3. So then you use your reasoning skills and you think, well, x minus 3 has a factor in the numerator, x minus 3 has a factor in the denominator. I could just cancel those, right? So we cancel them. And now we plug in what happens when x equals 3. Well, in the numerator, 3 plus 3 is 6. In the denominator, 3 plus 1 is 4. And so the answer is 1.5. State whether the function is continuous at the limit point. Well, no, it's not continuous, right? Because it's undefined. It's not technically continuous if we want to split hairs about it. So there's a hole there. But the discontinuity is removable. It's easily removed. It's a little hole in the function. All we would have to do is say, okay, here's a new function, and if x is not 3, use the function we're talking about, and if x is equal to 3, give the value 1.5, right? That would be a nice continuous function. If I want to, I can remove the discontinuity and just write x plus 3 over x plus 1. And now the green curve is a nice curve that's exactly the same as the previous one, except now I can plug in x equals 3. And the discontinuity is removed, going from red to green. So in my experience, whenever I talk to teachers who teach pre-cal, right, in pre-calculus, you do rational functions and you do these things where you find the holes by looking at the factors just like this. And pre-cal teachers will tell you, oh, the function is undefined here. But if you talk to people who like are actually mathematicians and do like, you know, analysis, that's their real job, they don't consider things like this to really be a discontinuity because it is removable. And if you remove it, then it's a nice analytic function and it's good. So honestly, I'm not going to take off points on a test if you tell me that this is continuous, because removable discontinuities are just, they might not even be there. They might as well not even be there if you can just cancel out the factors. Regardless, here's a new question. New limit, evaluate the limit numerically using a calculator. This time, my limit has me approaching positive infinity. And so what I might do to evaluate the limit numerically using my calculator is plug in the biggest number you can think of, x equals 1,000, and find out what it is. And then multiply that by 10 and plug in x equals 10,000. And then multiply that by 10. Plug in x equals 100,000 and tell me what number we're approaching here. And I'm going to try to save class time. I could plug this in my calculator, or I could just use Excel and to save class time, we'll just figure out what Excel has to say about this. Obviously, I can't plug in x equals infinity, but I can plug in x equals 100, 1,000, 10,000, 100,000, and so on. And my function is x squared plus 2 times x minus 5 divided by x cubed minus, open parentheses, x cubed minus 2 times x plus 100. Do you know what the capital E means?
Scientific notation.
Mm-hmm. Yeah, this is 1.00002 times 10 raised to the power negative 5. So it's the same thing as 0.00001000002. And so you can kind of probably get a feel for this. Like, what number am I approaching here? That was weird. What number is this limit approaching? 0. Yeah, I can tell by just taking larger and larger values of x that my number is getting closer and closer and closer to 0. And so that's pretty good evidence. That's what I mean when I say evaluate the limit numerically. Now let's evaluate this limit visually. And visually is going to mean going on Desmos.com and typing in x squared plus 2x minus 5 over x cubed minus 2x plus 100. Okay, so visually the question is, as I let x approach infinity, which means as I scoot farther and farther and farther to the right, where is this curve going? Is it going up? Is it going down? Is it settling out at some number? And as far as I can tell visually, it's getting closer and closer to 0, right? So that aligns with what we found numerically. Then analytically, let's talk about this. Because for a mathematician, plugging numbers in a calculator numerically is like evidence for what this limit is. Looking at the graph of it visually is like evidence for what the limit is. But a real mathematician, if you told them after looking at it that the limit was 0, they would ask you, how do you know the limit is really 0? How do you know the limit is not 1 times 10 to the negative 9th? Right, like it could be something besides 0. We haven't really proven that yet. And so for a mathematician, proof is really important, and that's what we're talking about here. How do I know that this limit is going to go to 0? Well, I could divide the numerator and denominator both by x cubed and see what we get. So then I'm asking about the limit as x approaches infinity. And if I divide the numerator and the denominator by the same number, then the fraction has the same value. I'm not changing the value of this function. So in the numerator, I'll have x squared divided by x cubed plus 2x over x cubed minus 5 over x cubed. In the denominator, I've got x cubed over x cubed minus 2x over x cubed plus 100 over x cubed. we can simplify this because x squared over x cubed is 1 over x. This is 2 times 1 over x squared. Or I guess I could have just written 2 divided by x squared. That's fine. And then this is minus 5 over x cubed. This is 1 minus 2 over x squared plus 100 over x cubed. And think about what happens to each one of these 6 terms individually as x is approaching infinity. If I let x get as big as it wants to, 1 divided by a trillion, 1 divided by a quadrillion, right? Imagine this x just won't stop growing. That number is approaching 0. Yeah, so all of these numbers are approaching 0. It's 0 plus 0 minus 0 over 1 minus 0 plus 0. The only thing that doesn't go to 0 is the constant number 1. So I've got 0 divided by 1, which is 0. And yeah, that's how I would show somebody if I was really trying to convince them that this limit was 0. But also, you probably remember this from pre-cal, that as long as you have a larger degree polynomial in the denominator, the limit's going to be 0. Right? The end behavior is going to flatten out at 0. As long as this degree is 3 in the denominator and 2 in the numerator, a larger degree in the denominator is going to give you 0 as the limit when x approaches infinity.
Is that only for positive infinity or for negative infinity as well?
That's for positive and negative infinities, yeah. State whether the function is continuous. So that question actually doesn't make any sense for infinities, right? We're not really concerned whether a function is continuous at infinity because infinity is not a number. Infinity is not a real number. And so we're not actually worried about these questions. If it says the limit as x approaches infinity, then don't worry about that. We're only worried about the continuity question when x is a real number. And infinity is not a real number. So don't worry about that. Okay. Similar thing, I can evaluate this numerically using a calculator by plugging in different values of x as x gets closer to infinity, meaning I plug in 1,000, I plug in 10,000, I plug in 100,000, however many times I need to get an idea. Or I can evaluate the limit visually using Desmos.com, right? You know, and just open up Desmos, plug this in and see what happens. We're going to skip to this in order to save some class time. And I already know that these questions don't matter for limits at infinity. So really, the only question I'm going to work for you on this example is evaluate the limit analytically. And again, we are going to tackle this by dividing both the numerator and denominator by x cubed. And what I will get is the limit as x approaches plus infinity of, what's 3x cubed divided by x cubed? 3. 25x divided by x cubed is going to be 25 divided by x squared, and then 5 divided by x cubed over, what's 4x cubed divided by x cubed? 4. And then 900 divided by x cubed. Well, in the limit, when I allow x to approach infinity, anything that's divided by x is going to shrink to 0. So the answer here is 3/4. Again, probably something you learned in pre-cal, right? that like if you've got the same leading exponent in the numerator and denominator, then you just take the ratio of the leading coefficients. And that's the end behavior for both x approaches positive infinity and x approaches negative infinity. But this is the explanation. This is like the proof of why we know that limit has to be what it is. Questions? Okay. Here's another one. Again, the last two questions don't matter because the limit is approaching infinity. And I could do numerically and visually, but those are easy. You guys can figure those out. What I want to do instead is ask the question, how could I figure this out analytically? And I'm going to divide the numerator and denominator, but divide the top and bottom by x. And we get the limit as x approaches infinity of x minus 25 plus 5 over x divided by 1 plus 900 over x. So in the limit, 5 over x is going to go to 0. 900 over x is going to go to 0. And in the limit as x approaches infinity, x becomes as large as it wants to. So large that minus 25 doesn't matter. And the limit as x approaches infinity is infinity. That's the answer. Again, you maybe learned this in pre-cal, but that's always going to be the case if the degree on the numerator is larger than the degree on the denominator for this exact reason. But the degree in my numerator is 2, the degree in the denominator is 1, and so I knew that this was going to blow up. This is a more interesting question. I'm going to give this one the full treatment, which means we're going to start off and talk about this numerically, like what would it look like if you plug this in your calculator. And to do so, we're going to try -6. We're also going to approach this -6 from the right side, and or maybe we'll do say the left side first. Call it -6.1. -6.01, -6.001. We're also going to approach this from the right side, which is -5.9, -5.99, -5.999. And then I've got to plug in my function here. This time my function is x squared minus 10x plus 25 divided by x plus 6. And so you can see the problem. Whenever I plug in x equals -6, the denominator becomes 0, and I can't divide by 0. So Excel tells me. Look at what's happening when I approach from the left side. -1200, -12,000, -120,000. Am I approaching like a constant, or am I approaching infinities? Yeah. On the left side, it seems like as I get closer to -6, it's approaching negative infinity. On the right side, as I get closer to -6, it looks like I'm approaching a positive infinity. And we can verify that visually. So we will. What I would like you to do is open up Desmos and take a look at x squared minus 10x plus 25 over x plus 6. and ask yourself, okay, at the point where x equals -6, that's the blue line, what's happening? As I get closer on the left side, it's going down to -infinity. As I get closer on the right side, it's going up to +infinity. So maybe you remember, but this type of discontinuity is called an odd pole. And obviously the function is not continuous, so I wouldn't be able to draw that whole curve without picking up my pen. When it says evaluate the limit analytically, this is hopefully something your teacher taught you in, what do you call it? Pre-cal? College algebra, whatever you want to call it. We could factor this whole thing and get x minus 5 squared over x plus 6. And then imagine you get any value x between -6 and 5. It will be the function value of this is going to be positive or negative. It's greater than -6, which means the denominator is going to be positive, and it's less than 5, which means this thing in the numerator would be negative, but then it's squared, right? A negative number squared is positive, so a positive over positive, it's going to be positive. And then any value for x less than -6, my function is going to be negative, because it'll be a positive divided by a negative. So on either side of x equals -6, the left side is going to be negative, the right side is going to be positive, for sure. And what happens as you get closer to x equals -6 is the denominator gets to be a really, really small number in terms of absolute value. And if you're dividing by a really, really small number, that gives you a really, really huge number. And since I can make the denominator arbitrarily small as I want to, by choosing an x value close to -6, then I can make the whole function value arbitrarily large. Everything up to infinity is fair game. And so this is how we know that by looking at this, when I have a factor with an odd multiplicity, by the way, I don't know if you heard the term multiplicity before or if it's just been a while. Multiplicity means like the power on the factor whenever you've got it in factored form. So this x plus 6 factor has a multiplicity of 1. This x minus 5 factor has a multiplicity of 2. But if I have an odd multiplicity in the denominator, that's going to give me an odd pole. What we're going to see in a minute is if I have an even multiplicity in the denominator, like this one could be factored as x minus 3 squared. Do you remember from pre-cal? An even multiplicity in the denominator is going to give me an even pole. And I'll show you what an even pole looks like. X minus 10 over x minus 6x, sorry, x squared minus 6x plus 9. This is what an even pole looks like. It doesn't switch plus or minus sign, precisely because the multiplicity in the denominator is an even number, right? It's not going to switch plus or minus sign, but it still goes to infinity. And so it's going to look, you know, like this. So this is an example of a discontinuity where there is an even pole. We would say, no, it's not continuous. And the limit, as x approaches 3 of this whole thing, is negative infinity. So limits can be real numbers, like 1.5 or 0. Limits can be positive infinity. Limits can be negative infinity. Also, I think I forgot to finish the last problem. Because in the last problem, we never said what the limit was. We said that this was going to be an odd pole, but what would I say about this limit? Since on the right side, my function was approaching positive infinity, and the left side, my function was approaching negative infinity. This is a case where the left side limit and the right side limit are different, so we say the limit does not exist. That's the answer to the question. This is what I want you to write on your test, okay? This limit, which is a two-sided limit, does not exist because the right side doesn't agree with the left side. So we say the limit does not exist. You could also write just DNE if you want to. And I'll understand that DNE means does not exist. Okay, consider the following limit. I'm taking the limit as x approaches 2 of x minus 2 divided by the absolute value of x minus 2. And so what happens if x is greater than 2? What is the value of this function if x is greater than 2? One. Because if x is greater than 2, the numerator is positive, and the denominator is positive because of the absolute value. And it's the same number. So positive divided by the same positive number must be positive 1. What happens if x is less than 2? Yeah. Because if x is less than 2, then now the numerator is a negative number. The denominator remains positive because of the absolute value. And so a negative divided by a positive is a negative, and it's the same number, so it must be a value of 1. And so this is another limit that does not exist. Because on the right side, everything is 1. On the left side, everything is negative 1. And so the limits are not going to ever touch. They're not going to agree there.
When you're saying on the right side and the left side, you're talking about when you graph it?
Yep, I'm talking about when I graph it. If I were to graph it, it would be x minus 2 over absolute value x minus 2. That's what the graph of the function looks like. Mm-hmm. And so imagine, like, right-sided limit. I'm approaching here from the right side. I'm approaching the value 1. Okay, left-sided limit. I'm approaching here from the left side. The value my function approaches is negative 1. So the right-sided limit doesn't agree with the left-sided limit. The limit does not exist. This is a case where both the right-sided limit and left-sided limit are real numbers, but they're not the same real number. And so the type of discontinuity is called a step discontinuity. And you can kind of see from the picture that it looks like you're just taking a step here from one value to the next. That's why we call it a step discontinuity. And so obviously the answer is no, the function is not continuous at this point. On to the next one. This one's pretty wild. Sine is a function that oscillates. As the argument of my sine function grows, sine is a function that goes up and then down and then up and then down and then up and then down from positive 1 to negative 1 to positive 1 to negative 1 over and over and over again, right? But what's in the argument of the sine function is not just x, it's 1 divided by x. And 1 divided by x grows to infinity as x approaches 0 from the right side, doesn't it? So whenever I consider the limit as x is approaching 0, it's really kind of like the limit as sine has an argument approaching infinity, right? The argument of my sine function is approaching infinity because x is approaching 0 and I've got 1 over x. And so what does the sine function do as you approach infinity? It just goes up and down and up and down and up and down and up and down, right? It doesn't approach any particular number. It also doesn't approach infinity. This is a limit that does not exist. If you tried to evaluate this limit numerically by choosing values that are closer and closer and closer to 0, you should not recognize any pattern. It should be just kind of a random sequence of numbers that just jumps around all over the place. If we have time, maybe we'll do that, but I'm trying to be efficient with my time. It is important to see this visually. You know, I'm trying to describe this to you before we put it in the calculator because it's good to develop kind of an imagination for these things. But let's go ahead and graph it. You can see what the heck I'm talking about, right? Since the sine function oscillates when x is approaching infinity, this is now 1 divided by x, so it's going to oscillate as x approaches 0. And so the closer we get to x equals 0, the more that this is going to oscillate. I wish there was a way to kind of zoom in the x direction without zooming in on the y direction. Maybe I can. But the oscillations just get tighter and tighter and tighter, and it does not ever slow down. So again, if you were asking about the limit as x approaches 0, it doesn't matter if you're talking about it from the right side or the left side. The limit just doesn't exist, right? There's not a single point that you're approaching. You're not approaching infinity. You're not approaching negative infinity. It's just getting wound up crazy. So no, it's not continuous at the limit point. And what type of discontinuity is this? It's not removable, right? I can't just define a value for the function at x equals 0 and then like we're happy, right? That wouldn't, nothing would make sense as a place to patch a hole. At a discontinuity, is it a step discontinuity? No, right? We didn't see a step happening. Is it an odd pole? No, there's no infinities involved. Even pole? Nope, same thing. This must be an essential discontinuity. So this is our first example of what it means to have an essential discontinuity. Consider the following limit. We're taking a limit as x approaches 0 of e to the 1 over x. And you can always try to plug in x equals the limit point and see what happens, but that's no good because I can't divide by 0. Let's do this numerically first. Let's first try to evaluate this limit numerically by plugging in some values into the calculator. See what we get. And my function is e to the power 1 divided by 0, or 1 divided by x, right? In Excel, that's exp for the exponential function. But coming in from the left side, I've got negative 0.1, negative 0.01, negative 0.001. Coming from the right side, I've got 0.1, 0.01, 0.001. On the left side, it's not exactly 0. The point is I'm trying to find if it says something besides 0 in this data type, but maybe it doesn't. The point I'm trying to make is this is not actually exactly 0. Computers are kind of limited in what you can calculate. Like this blows up too big for the computer to store the number, but we can make it more reasonable. As I approach 0 from the left side, small number, really, really small number. Ooh, super duper duper small number, right? That's 10 to the negative 87 power. So what am I approaching as I approach from the left side? 0. As I approach from the right side, I've got 22,000. I've got 2 times 10 to the 43 power. Oh, sorry, I got that out of order. That should be 0.005. There we go. 10 to the 86 power. These numbers are getting bigger. It looks like I'm approaching, yeah, positive infinity. So from the right side, we're approaching positive infinity. From the left side, we're approaching 0. Remember, this is my notation for right side limits and left side limits. And if the right sided limit doesn't agree with the left sided limit, then the limit does not exist. Is the function continuous at the limit point? No. What type of discontinuity is this? Well, it's not removable. It's not a step because I've got an infinity. It's not a pole because a pole would require both to be infinities. So this must be essential. And again, always, when you're doing your homework, always graph everything on Desmos. It will make you smarter to graph things on Desmos. You can understand what the picture looks like. Remember this e to the 1 over x function. Okay. Consider the following limit. We have the limit, as x approaches 0, of sine of x divided by x. Let's evaluate the limit numerically first. So, my function is just sine of x divided by x. First, we're approaching from the left side with the negative numbers. What number am I approaching?
1.
It appears to be a 1. On the right side, also appears to be a 1. So even though I can't divide by 0, it really appears numerically that this is a 1. Let's graph it visually. Sine of x divided by x. It's one of my favorite graphs because I think it just looks really nice. I'll make the y-axis a little bit taller. And sure enough, as we approach 0, it looks like this function should have a value of 1. It just has a little hole there, right? But if a discontinuity is easily removed, that makes it a removable discontinuity, we could just say the value of this function is 1, right? You just say at x equals 0, this function has a value of 1. So what type of discontinuity? This is a removable discontinuity. And in practice, you would just remove it by saying the function has a value of 1 when x is equal to 0. So we saw it numerically, we saw it visually. I told you before that for like a mathematician, if you were, working in the world of mathematics, you could show people this and you could say, listen, this seems to be a lot of evidence that this limit is the number 1, right? Like we're getting really close numerically. We got a graph of this thing on Desmos that looks like it passes through 1. There's a bunch of evidence in favor of this thing being a 1. But in the world of mathematics, a lot of things are misleading, right? You can't just trust your gut. Everybody is looking for a proof of how do we actually know that this is true. And this is like one of the most important proofs in calculus. Especially imagine yourself back in the day when you're like Isaac Newton, 300 years ago. You don't have Desmos. You don't have computers. You don't have calculators. How are you going to prove to all the other mathematicians in Europe that you figured out this limit? And this is one of the coolest proofs, I think. Maybe that's just my opinion, but I think it's really, really cool. What we're going to do to prove that this limit is equal to 1 is I'm going to sort of draw an xy plane. And I'm going to do my best to draw the unit circle. That's supposed to be a circle. And I'm going to draw a little triangle here. So that this is 1, right? It's a unit circle. So the hypotenuse of the triangle is 1. This is going to be an angle x. This is a right angle. This vertical length is going to be what? What trig function? Sine of x, yeah. Now, what you probably know about measuring angles and radians is that, like, for a unit circle, this little arc length from here to here has a length x. If I measure this angle in radians and I say this is an x measure of angle, then this blue arc has a length of x. Because the whole circumference of the circle is 2 times pi times the radius. The radius is 1, so the whole circumference of the blue circle is 2 pi. But when we measure an angle in radians, a full rotation is 2 pi. And so that means measuring an angle in radians gives you the length of the arc on the unit circle. So I've got this orange vertical distance sine of x. I've got this blue curve x. And then it's going to be really difficult for me to draw this, but I'm going to try. I need another straight line. Straight lines are the hardest. And we are going to make it go here to here. And I'm drawing the straight line so that it makes a right angle with the hypotenuse of the orange triangle. So that now this, the side length of 1, if I look at the green triangle, that's no longer the hypotenuse, because the black side along the x-axis is the hypotenuse of the green triangle. Instead, for this angle x, the green side is the opposite side. What trig function will give me the ratio of the opposite side to the adjacent side? Tangent. So tangent of x is the length of the green side. Because that's the ratio of the opposite side length of the angle x to the adjacent side length. And the adjacent is 1. So right, it would be tangent of x divided by 1 is still tangent of x, yeah. So what we have here is this picture. I think we can all agree that orange is going to be the shortest blue is going to be in the middle, and green is going to be the longest of these lengths that I've kind of highlighted. So remember, the orange vertical is sine, the blue is x, and then the green is tangent of x, the way that I've constructed this picture. The next thing I want to do is I want to divide everything in this inequality by sine. So that sine of x divided by sine is 1. X divided by sine will be x divided by sine. And what is tangent? Well, tangent is just sine divided by cosine. So what's sine divided by cosine divided by sine? 1 over cosine. Now, next step, take the limit as x approaches 0. Well, for the constant, the 1, it gets to stay a number 1. I don't know what the limit of x divided by sine of x is as x approaches 0, because sine of 0 is 0, so we leave that alone for right now. What about 1 divided by cosine of 0? What's cosine of 0? 1. So while we don't really know what the blue limit is, I do know that it has to be between the number 1 and the number 1. So yeah, exactly. This is the proof. This is how mathematicians first figured out that the limit of x divided by sine of x is 1. And then what's the reciprocal of 1? What's sine of x divided by x? It would also be 1, right? 1 divided by 1. So anyways, I think that's a really neat proof. I think it's cool. Not very many things in math are like genuinely cool to me, but the fact that somebody thought through that for the first time It's got this nice geometric element where it relies on our knowledge of triangles and circles and stuff. I like it. Consider the following limit. The limit as x approaches 0 of natural log of x. So if I wanted to evaluate the limit numerically using a calculator, I would take the limit of, the natural log of 0.1, and then I would take the natural log of 0.01, and then I would take the natural log of like 0.001 and see where those are going, right? Guess where that's headed. I could evaluate the limit visually using Desmos.com, right? You can graph it and look at the curve. Let's talk about this first analytically. What we know about the natural log function is that if I have a function equal to e to the x, the definition of what it means to be the natural log function is that it's the inverse function of e to the x. And to remind you, e to the x is a curve that is always positive and strictly increasing, and it grows exponentially, right? So it's very flat, barely increasing on the left, and it's very steep and very quickly increasing on the right. And when I have e to the 0 power, like when x is equal to 0, e to the 0 power is 1. And maybe you remember this from your pre-cal or college algebra or whatever, but inverse functions have a symmetry about this line, y equals x. And so the bilateral symmetry of this function means that it's going to pass through the point 1 on the x-axis. And it's going to be strictly increasing, but very, very slowly as I go to the right. And again, if I've got a mirror bilateral symmetry across this blue line, then that means the curve is going to get closer and closer and closer to the y-axis. Just like the orange curve gets closer and closer and closer to the x-axis. And this would be my natural log curve. Whereas this was my e to the x curve. But they're supposed to have this mirror symmetry. And so knowing this, I can think about it, use my reasoning skills, right, to say that this limit of the natural log curve as x approaches 0 is going to be what? Negative infinity. And I know that whenever we talk about limits, I told you that the limit is really the two-sided limit, and the right-sided limit and the left-sided limit have to agree. But if you look at this purple curve, it exists on the right side, and it just doesn't exist on the left side. And so it would be natural for somebody to talk about this and say, oh, it's the limit as x approaches 0, even though it's only a one-sided limit. Even though this is technically just a right-sided limit, I feel like you could write this either way, and people would know what you're talking about. So you don't necessarily have to put the little plus sign here to say it's a right-sided limit, because it's the only sided of the limit. I don't know. So I won't, obviously I don't care. I don't care whether you want to say x approaches 0 or x approaches 0 with a little plus sign. Either way is fine in this case. It's unambiguous. So obviously it's not continuous at this point. The type of discontinuity would be an essential discontinuity. Remember, because if it were a pole, you would also have the function appear on the other side of the discontinuity as an infinity, but we don't, so this would be considered essential. The next thing is limit properties. Limits have nice properties that make them really easy to work with. If I'm taking the limit of two functions and I'm adding them or subtracting them, okay, you can just break that up into two different limits. Take the limit of each term individually, right? If I'm multiplying two functions on the inside of a limit, just take the limits separately, right? That's totally fine too. If I am dividing a function, right, on the inside of a limit, I've got f divided by g. Just take the limit of f and the limit of g. That works as long as g does not have 0 as the limit. If the limit of g is 0, then you can't apply that division rule because you can't divide by 0, so you need to think about it a little bit more. And the next thing, the fourth line here, I will say it's just an application of this multiplication thing. An exponent like n is just repeated multiplication, right? And we already said in multiplication, we can just take the limit of each factor independently. And so if I have limit of f raised to some power, you can just bring that some power outside of the limit, take the limit of the f function and raise it to that power. So hopefully these limit properties are things you would expect. It's ways that limits behave nicely. There's nothing surprising. With the derivatives, you know, derivatives had the additivity property where you could take the derivative of each term individually, but derivatives did not play well with multiplication and division. That's why we ended up with the derivative product rule and the derivative quotient rule, but you don't have to worry about that with limits. The rules are a lot easier in the limits game. And then if I want to compose functions inside of a limit, it works exactly like you think it would. In a function composition like f of g of x, you can first take the limit of the g function on the inside and then plug that in to the argument of the f function. So there's no limit chain rule the way that there's a derivative chain rule. Limits also play really nicely with composite functions. And so that's like good news, right? That makes it easy for us. The caveat here, I guess, is that your outside function f has to be continuous at the limit of the g function. And if the f function is not continuous there, then you have to take a step back and think a little bit harder about it. But supposing that the outside function is continuous at the limit of the inside function, then you're good. So, consider the following limit. There it is. The limit as x approaches 0 of cosine of pi times sine of x divided by 4x. Okay, forget about the numerically stuff. We're going to just think about this for a minute and talk about it. So we're concerned about this. This limit is the same as the limit as x approaches 0 of cosine of pi over 4 times sine of x divided by x. So the first thing that I'm thinking about is the last thing we just mentioned. These are composite functions, right? I've got cosine of a bunch of stuff on the inside. So I've got like an inside function and an outside function. I'm composing two functions. And so I know that limits work really well with composite functions as long as the outside function is continuous at the limit of the inside function. But my outside function was cosine, And cosine is a continuous function. Cosine is continuous everywhere, right? There's no discontinuities in cosine, and so this is going to work just fine. I'm going to move the limit inside of the cosine. And I'm allowed to do that because cosine is continuous everywhere. And then on the inside of this limit, I'm multiplying two things. So I can take the limits of these two factors separately and then just multiply what I get. So the limit of pi over 4 as x approaches 0 is just pi over 4. And then what's the limit of sine of x divided by x as x approaches 0?
Infinity.
Would it be undefined?
One.
Yeah, this is the last thing we talked about yesterday, right? It was the cool geometric proof. But the limit as x approaches 0 of sine of x divided by x is 1. So
Why is the limit of pi over 4 just pi over 4?
well, because pi over 4 is a constant function, right? Let me graph it for you and you'll understand. If I say y equals pi over 4, and I ask you what's the limit of this function as x approaches 0, right? Then from both sides, the limit is pi over 4. Yeah, so the limit of a constant is just the constant when there are no x's involved. So what is cosine of pi over 4? Cosine of pi over 4 is square root 2 over 2. So, again, this is kind of an interesting question, right? Because if you tried to plug in x equals 0, of course you get sine of 0, which is 0 divided by 0. 0 divided by 0, you know, that doesn't mean anything to us. That's not a number. And so I can't take cosine of 0 divided by 0, and so it's not really clear what this limit is going to be until we sit and think about it. And after sitting and thinking about it and applying our limit rules, we find that that limit should be square root 2 over 2. And then we can plug this into Desmos too, and we'll see what Desmos has to say about this. This is a good way to check your answer. Okay, so that's what the function cosine of pi sine x divided by 4x looks like. It's kind of a boring function. And my claim is that as x approaches 0, notice Desmos doesn't know how to calculate that by taking the cosine of 0 divided by 0. But we could find that the limit is square root 2 over 2, right? Square root 2 over 2, that's the blue line. So sure enough, that looks like a good limit. This is called the squeeze theorem. And it says, suppose that I've got some interval along the x-axis. So here's my x-axis, and I'm concerned about the interval between a and b. And across this entire interval, we've got a function f a function h, and another function g. And suppose that for some value of c that sits in between a and b, so maybe this is the point c, my function f and my function h have the same limit. Do you see how the picture I drew, the function f in blue and the function h in orange, they have the same limit as x approaches c? If f and h have the same limit, then g, the function squeezed in between them, also has to have the same limit. So this is the picture that I want you to have in mind whenever anybody mentions the squeeze theorem. Imagine you've got a function on top, a function on bottom, and they're going to squeeze down to the same limit at some point and then diverge again. And importantly, if you know there's a third function, like the purple g function, that's always in between those two, then it has to have the same limit. And by the way, this is exactly what we talked about at the end of class yesterday. I didn't really give it a name, but do you remember this proof when we drew my right triangles, and so I labeled the one that's sine and the x and the tangent of x, and I said, well, my function x is always greater than, and I really should have said greater than or equal to. I said x is always greater than or equal to sine, and it's always less than or equal to tangent. What I'm trying to do in this proof is I'm trying to build up a squeeze theorem, right? I'm trying to say divide by sine so that 1 is less than or equal to this function, which is less than or equal to that function. Take the limit of each of these as x approaches 0. And we didn't know what 0 divided by 0 would be, but I do know that 1 divided by cosine of 0, 1 divided by 1 is 1 in the limit. And so this is an example of how we applied the squeeze theorem here, because I had a function that was squeezed in between two other functions at the limit point. That's the only way we were able to take this limit. Okay, so that's one example of using the squeeze theorem. I'll show you one more example real quick. And this will be the last thing in section 3.4. It says, consider the following limit. We're taking the limit as x approaches 0 of x squared times cosine of 1 over x. And if I just try to immediately plug in x equals 0, then I'm going to get something like 0 squared times cosine of 1 divided by 0. And the problem is I don't know what 1 divided by 0 is. That's not a number. So that's not going to work. Instead, consider how cosine of anything is always strictly between -1 and +1. Remember that? My cosine curve is just going to bounce from +1 to -1 to +1 to -1 to -1 to +1 to -1, everywhere in both directions. So it doesn't matter what you plug in for the argument of cosine. Cosine always has to be between -1 and +1. Let's multiply everything by x squared. So on the left, I get -x squared is less than or equal to x squared cosine of 1 over x. And on the right, that's less than x squared. Now, take the limit as x approaches 0. And the limit of negative x squared as x approaches 0 is 0. What's the limit of x squared as x approaches 0? 0. So using the squeeze theorem, what's the limit of x squared cosine 1 over x as x approaches 0?
Probably 0.
The answer here has to be 0 because of the squeeze theorem.
But then we just try 0 and it didn't work up there.
Yeah, that's the whole idea with limits, right? Is most of the time you can't directly evaluate what the limit will be. That's always, the case with any of these. If I tried to directly evaluate any of these we did in class, like taking the limit as x approaches 2 would give me 2 minus 2, which is 0, divided by 2 minus 2, which is 0. I'd end up with 0 divided by 0. That's the big idea here, is that even in these cases where trying to directly evaluate something at a point, like this one, setting x equal to 3, gives me like 9 minus 9 divided by 9 minus 6 minus 3. It's 0 divided by 0. But it really had a limit, Even when you cannot directly evaluate the limit by plugging in x equals the limit point, you can still say something smart about what the limit will be, right? Like, I can't plug in x equals 0 and get sine of 0 divided by 0. That'd be 0 divided by 0. That doesn't make any sense. But it still has the limit of 1. These are the things we're most interested in. So let me graph this for you. I'm going to graph x squared cosine 1 over x. And this is what x squared cosine 1 over x looks like. I'm also going to graph on the same graph y equals x squared and y equals negative x squared. Because the cosine function just bounces back between -1 and +1. And so I expect that this purple curve is just going to bounce back and forth between the top orange curve and the bottom orange curve. And that's kind of what we see happening, right? The purple curve is just going to kind of bounce between these. And so the idea of the squeeze theorem is that, well, the top orange curve and the bottom orange curve both have the same limit as x approaches 0. And since the purple curve is always sandwiched in between those, the purple curve gets squeezed down so that it has the same limit. The limit was 0 in this case.